So one of the things that was not supposed to show up on the test, because I had intentionally removed it from the slides and put it into this unit, and then for some stupid reason left it in the exam, okay, was that question about isoelectronic, okay, which we made as an extra credit one. We had more than 100 points, so that was part of that 100 points, or those extra 100 points. Isoelectronic is just referring to same electrons. That's it. Okay? So if I wanted to look at fluorine, okay, what would its electron configuration be? So there's two approaches that we talked about. One is the long way, you just start plugging in electrons into each of our orbitals, and we just remember how to fill that out, okay? Which would be 1s, 2, 2s, 2, 2p, 5. We add up the superscripts. 2 plus 2 plus 5 gets me 9, which happens to be the atomic number of fluorine. So for a fluorine atom, it has 9 electrons, and that works. The other approach is we could use the periodic table. Where is fluorine? It's in the P block. I heard someone say it's in the second row. So second row is our second energy level. It's in the P block. And it's in the fifth column of the P block, so it's 2p5. I know that's its last thing. Everything else before it has to get filled. Okay? Which would mean 2s2, 1s2. We end up with the exact same answer, depending on how we wanted to approach this, going from the very last electron or the very first electron. Okay? So that's our electron configuration for fluorine. What if we made that fluoride? That's an interesting dilemma, because that's now nomenclature, which you're all experts at, because you watched a friggin' mile-long video on that. And fluoride is F minus. How do we become F minus? We have to add an extra electron. Why do we add an electron? It says it's negative. Electrons are negative. Okay, so we have to be careful with the sign when we're manipulating these things. So if I have an extra electron, instead of there being 9 electrons, there are 10 electrons. Can I put that extra electron into the 1s orbital? Why not? Can only fit 2, so I couldn't possibly fit it there. How about the 2s?
No.
Can only fit 2. There were already 2 there. How about the 2p? Yeah, I could put it there, and my total becomes 2p6. That's now the electron configuration for F minus. Okay? Theoretically, this was something you already knew how to do. Okay? You knew what the charge meant. You knew what the electron configurations were. You just fill it out. Okay? What if I had said the fluorine cation? A cation is positively charged. How do I become positively charged? I take away an electron. Where would I take that electron away? The highest energy electrons, which would be in the 2p. My electron configuration, 1s2, 2s2, 2p5. Sorry, 4. Good? Okay. We then encounter this concept of ionic charges. And that if we look at fluorine in this periodic table, it says that it is -1. Saying nothing about it being +1. So, well, what's going on with that? Well, chlorine says it's -1, and bromine's -1, and iodine's -1. Okay, interesting. Everything in the same family has the same number of charge. Would we expect that to be true? Yes, because it's in the same column. Remember, we get trends of chemical reactivity within the column. That's why we call them groups and families. This was the whole power behind Mendeleev's periodic table and the organization. Okay? So if I can determine what one of those is going to be charged, everything in that column should be that same charge. And if we go through and take a look, that kind of matches to the rest of the periodic table, at least for the ones that are specified. Okay? So now the question becomes, well, if I had the option to be F plus versus F minus, wouldn't you rather have an F plus than an F minus? Why is it preferentially going to F minus and not F plus? What's that?
Because the obvious level is more full.
Okay, well, more full on its own kind of works. That gives us more symmetry, but we can use less science in that description. Yes, and then yes.
Has more electronegativity.
Electronegativity can explain why it should take an electron. That doesn't explain why it only takes one.
Because it becomes more stable.
What do you mean more stable?
Because the noble gases are the really stable ones, and they have 8 valence electrons.
There's a key word I'm fishing for. The noble gases. What do we know about the noble gases? They're noble, and they were noble. We called them noble because they don't react. Okay? So everything, excuse me, if we use that name and we think back to us as humans, let's try that again. Do you want to become like the nobility? I mean, what do they have? Tons of money, tons of power, no chemistry class. Okay? You're probably saying, yeah, being like the nobility is pretty awesome. Okay? But to be like the nobility, I have to have all this money and all this wealth, all this power and all these things. Okay? What can we do in the meantime until we get there to look like the nobility so that we make everybody else think we are noble? What's that? We, personally, people.
Treat yourself, buy good stuff, expensive.
Okay? Treat yourself. Instead of wearing crummy clothes that you got from Goodwill, you could go out and buy really nice, expensive clothes. Okay? Can you afford it? No, but that's what a credit card's for. But at least everybody thinks I look wealthy. Okay? When I go rolling out to the club, I'm not going to show up my dumpy little, what's a cheap car? Well, I got a Honda Civic, so let's say that. Wouldn't roll out to the Honda Civic. Okay? I'd probably go to the dealership and say, yeah, I want to, test drive that Mercedes, for the weekend. Okay, sure, you can go ahead and do that. We just need a $5,000 deposit. Okay, here's my $5,000. Woohoo! I now have a Mercedes, and I show up at the club and everybody thinks I'm awesome. Okay? Do I have any of that money? No. Okay? But now everybody thinks I look rich. Okay? That public perception is the exact same thing our elements are doing, believe it or not. There's only 3 things that our elements have access to, though. Protons, neutrons, and electrons. What happens if we change the protons? Changes the element. So if fluorine wants to look like a noble gas, if it takes an extra proton, is it fluorine anymore? No. Okay? So I can't change the number of protons because that changes who it is. Okay? I can change the neutrons. Okay? But do the neutrons define which element we are? No. Okay, so that only leaves one option. The electrons. I can change the number of electrons. I can change how the outside world perceives me by changing the electron shell. And when I change that outer shell, I can now look cooler. I look more symmetric because I'm fully filled. And now everybody thinks I'm awesome like a noble gas. Okay? And of course that backfires. We run into debt, or in the case of fluorine, we're a super reactive molecule. Right? But we're attempting to look like something else. That's the same electrons. So why is fluorine, chlorine, bromine, iodine all trying to look like the noble gas immediately next to them? If fluorine gains 1 electron, it becomes 2p6. Okay? Which means second energy level, P block, 6th column. Fluorine's looking like neon. Okay? What would happen with chlorine? Well, it looks like argon. Bromine looks like krypton. Okay? We're looking like those noble gases. Why did fluorine decide to look like neon and not, say, argon? To look like neon, what does fluorine have to do? Gain 1 electron. To look like argon, what does it have to do? Gain 9. I'm willing to go out to the club and look like I've got a lot of money, but I'm not about to spend 20 grand on a Lamborghini rental when I can spend 5 on a Benz. Okay? Same thing's happening with our elements. Okay? They're willing to accept extra electrons to change their configuration but they can only do a little bit. Fluorine, chlorine, bromine, and iodine are only willing to accept 1 electron more. Okay? They won't accept more than that because they'd have to accept a whole lot more to look like a lower noble gas. Make sense? Could they have done the reverse? What's the reverse? How about giving it away? Could fluorine have looked like helium? Helium, it could absolutely look like helium, but to look like helium, what does it have to do? It has to lose 7 electrons. So which is easier? Lose 7, gain 1. Gain 1. What happens? Fluorine gains 1. So what happens when we now look at it as an ionic compound? Okay. Number 1, I predict it to be an anion or a negatively charged species because it's going to gain an electron. It becomes negative. Right? The scale of that negative is only 1 because that's all it needs to look like the neon. What happens if I move to oxygen? Well, we know the answer. What does oxygen do? It gains 2 electrons. Right? It tells us that right there. Okay? How could we predict it? What is oxygen trying to do? Look like neon. Oxygen has 8 outermost electrons. To look like neon, it needs 10. So what do we have to do? Gain 2. What else could it have done? Lost 6, which is easier. Lose 6, gain 2. Gain 2. So oxygen becomes an anion, gains 2 electrons. Make sense? So what happens in nitrogen? Gains 3. The other option would be? Loses 5. How are we? All on the same page? We're hearing a lot of people over here saying answers, and I'm not hearing so much over here. Are we on the same page? You guys get it?
What is it losing 5 to get to?
What does oxygen, what did we say? Nitrogen? So let's take a look at nitrogen's electron configuration to answer that. 1s2, 2s2, 2p, 2p3. If we lose 5 electrons, there's 3 gone. There's 2 more gone. I would have the electron configuration of 1s2. What element has only 2 electrons? Helium. Is helium a noble gas?
It's just trying to be a noble gas.
It's just trying to get back to the noble gases. Okay? Okay, because I didn't hear as much of a chorus over here, we'll throw you guys the curveball. What charge do we expect for carbon? This one's extra tricky because it's not on the table. I didn't ask you this side.
It could be either, because it's the same distance.
Carbon. That's technically true. Carbon, to look like neon, what does it need to do? Gain 4 electrons. To look like helium, what would it need to do? Lose 4. Which is easier? They're the same. So what happens? It can go either way. Right? Does it go either way? Absolutely. It actually goes anywhere between -4 and +4. Right? So why are we not telling you that on this chart?
Just kind of know it.
Say that again.
We don't know for sure what it's going to go.
We don't know for sure where carbon's going to go. All of the charges that are specified on this chart are sure. They're, I'm going to get in trouble for saying this, guarantees. Okay? Let's add the caveat on that. If they are ionic compounds, they will hold those charges. Okay? And because they always hold that charge, it makes sense to memorize them. Okay? Did we have to memorize them? We just predicted what all of those charges were based on knowing them looking like the noble gases. We don't have to memorize that. We can remember that our charges are based off of looking like noble gases. We've eliminated the memorization aspect. Okay. Granted, that was only for the negatively charged species. We have positive charges, and positives are opposite of negatives, so of course the positively charged species are going to be a whole new rule, because that's just what science does, right? What would we expect to happen to magnesium? What are its 2 options? Magnesium has 12 electrons. It can gain 6 to look like argon, or lose 2 to look like neon. What does it find easier? Lose 2. Guess what happened? It lost 2, and it became positive. The exact same rule that allows us to predict negatively charged species allows us to predict positively charged species. Okay? We don't have to have these absolutely memorized. Right? We've got the derivation from it if we understand our electron configurations and some basic principles behind our noble gases. Yes?
So they're negatively charged if they have to go backwards to, well, backwards to be noble.
Front, forwards, and backwards is, I think, just going to be confusing. I can't even deal with left and right. Okay? So they are negatively charged because they are gaining electrons.
Okay.
They are positively charged because they are losing electrons.
And that explains the n, if it were n plus 3 to be neon, or minus 3, right?
For nitrogen, it would be a negative 3 charge because it gained 3 electrons. Okay? One option is potentially envisioning it like a cylinder. I don't think the cylinder is the best option. I think the way we describe this works out better, and I will probably end up deleting the cylinder argument for all future cases. Okay? There are a couple kind of brutal exceptions to this. So we just kind of defined the elements and what their charges should be. Everything up here is something that you need to know. Okay? I would cross out tin and lead. You are not required to know those. Not all tables are perfect. Aluminum, you're required to know, but aluminum fits the pattern. There are 3 more elements that you should know. What are those 3 more elements? Because I believe they were in the video. Could be wrong. No.
Oxygen?
No. Oxygen's already one on there. Carbon, no. That's one we said you don't have to memorize. Sulfur is under oxygen. That's one we have to memorize. Copper, no. Zinc, there's one. Zinc, yes. Zinc is one you are required to know.
Lead?
Silver, yes.
Lead?
Cadmium. You are required to know those 3 in addition to these. What is the zinc and cadmium? Before you take a picture, let's actually finish out the charges. What are the charges that we need to remember for these? Zinc is a +2. Cadmium, being directly under zinc, is also a +2.
Why are they plus 2?
You don't want the answer to that.
Okay.
Silver,
Plus 3 or minus 3?
+1. Okay? If you do actually want the answer to the specifics of why they're +2 or +1, talk to me after class. It's a lot more complicated. That whole symmetry argument that we've made a couple different times comes into play, but it becomes a lot more difficult because we're now looking at the transition elements, which brings in the d orbitals, which throws a massive monkey wrench in our interpretations. So everything up there, you need to have those charges memorized because we need to know those because that will allow us to solve for the other elements. So we have to know those. Okay? We good?
Yes.
Still see a couple pictures? Yes?
I just had a question. Is there a reason why the alkaline earth metals are not?
Well, what about the alkaline earth?
I'm sorry, or not the alkaline,
These guys? The transition
I
elements?
forget the name for it, the green,
The metalloids?
yeah, the metalloids.
Why might the metalloids not be included in this?
Because they can be
What is the charge on most of our metals? Take a look at the metals. What's our charge? Positive. What's our charge on our nonmetals? Minus. What's happening between the metalloids?
to become branching the gap between metals.
They are bridging the gap between metals and nonmetals, which mean their properties overlap. Sometimes they come out as acting more like nonmetals. Sometimes they come out acting more like metals. So you're not required to memorize the metalloids because they can get a bit dicey on you. when it comes out to those charges, because it's that bridging section. Okay. Other questions? Okay. Compounds and chemical formulas. Guess what we have here? It is a compound that involves what elements? Carbon, hydrogen, nitrogen, oxygen. Anybody recognize it? It's not air. It's not alcohol. That one's too simple. What was that? Caffeine. It's the structural formula for caffeine. I don't expect you to know that, but what I do expect you to do is recognize that this is kind of a confusing thing to look at, right? Do you want to spend the rest of the semester drawing out structures like this? Okay. Probably not, okay? Because what we will spend most of our time doing is ignoring structure for the most part, okay? And we'll be focusing on the quantification of chemistry, meaning looking at numbers, the amounts of things, the different units associated with those numbers, the uncertainties with those numbers. Okay? So we tend to ignore the structural part, okay? Which is why I get so irate when we talk about structure, because most general chemistry classes ignore it. We've spent a significant amount of time talking about Lewis structure, which is why it showed up on the exam, which is why it will show up on the next exam. Okay? So if you had a hard time drawing out those Lewis structures, guess what you should do? Keep practicing, because I guarantee you they will show up on the next one. Okay? So how could we simplify this to get rid of the structural information but still maintain some information that's included there? As a hint, how many carbons are there? I got 8. How many hydrogens are there? How many, I don't remember the order. Nitrogen? Oxygens? And we could now refer to caffeine by its formula. What are the elements that made it up? Okay. Our carbon, hydrogen, carbon. Turn into a pirate all of a sudden too. Nitrogen or oxygen. We can specify the amounts of those elements. That's what the subscript meant, right? The 8 after the C means there are 8 carbons in that structure. The 10 after the hydrogen meant 10 hydrogens. So our subscript refers to the thing directly in front of it. Oh, that was supposed to disappear. That worked out really well. Right? So we could go through and look at these formulas. Right? Slight variations. Okay? Notice that we're differing the amount. Right? We could start changing, jerk the slides. Anybody notice a difference between these two? What's that? The numbers of each of the elements are the same. Why would I shuffle the order around?
There's different compounds, right?
It could go back to different compounds. It's coming back to trying to organize the different elements in such a way that we could predict the structure. Okay? Trying to provide some clue to that. As far as you guys are concerned, all you have to do is provide a list. How many carbons? 2. How many hydrogens? 4. How many oxygens? 2. All 3 of those are equivalent. You do not have the ability to differentiate and say why one is better than the other. So don't stress about that. Just interpret what the formula means. In all 3 of those cases, how many hydrogens are there? 4. How many carbons? 2. How many oxygens? 2. So it's just a question of recognizing where the element is and counting it up. Okay? Don't panic about the order or the sequencing.
Okay, could we like write it as like more like
Yeah. So I believe what you're asking is, could we ask, instead of saying it out like this, that we did something along these lines?
Yeah. Yeah.
Okay. Can you, to interpret the formula? Absolutely. Can we as a scientific community now switch to that format? No, not a chance. Okay? Too many old dead people. Okay? We're going to have to stick with the format written. If you're having a hard time understanding how that horizontal version interprets, rewrite it in the vertical line, put the numbers out in front, do whatever you got to make sure you interpret that correctly. And that is absolutely fine. Okay? Last quick thing before we move on. What's happening down below? We're now doing a chemical reaction. We add hydrogen to oxygen to produce water. Okay? So the chemical reaction is going to take the information from our formulas and start to compartmentalize and put that into a situation that is chemistry, running a reaction, mixing things with each other to make something else. Okay? That is officially the next level interpretation. First, we've got to deal with how we get those formulas, okay, and how we talk about them. That is the nomenclature video that I should have some more slides on. So we may be kind of dancing in the dark on that one. Yes?
Why is it 2 oxygens and not 1?
For
Hydrogen, I feel like when you create water, like isn't it?
There's an interesting question. When we look at this formula, you're saying, why does that say O2 and not H2 plus O? Anybody know? It's still unbalanced. It's actually more unbalanced. If we erase that 2, it becomes balanced, right?
2 hydrogen and 2 oxygen equals 2 water molecules.
Okay. This does not address anything with a balanced equation. So you may have heard something about balancing. This is not balanced. Didn't ask for it to be balanced. It's just looking at the general pieces. Why are we specifying it as O2? When we look at oxygen or some elements as atoms, they don't appear as atoms. They appear partnered with one of their like elements. Those elements are known as our diatomic elements. And I really wish I remembered where on the slideshow it is, because I would advance to it. But I think it's a sizable way through the slides, so I'm not going to try and search for it. Okay? But we will address that. Oxygen happens to be a diatomic element. Same deal with hydrogen, which means anytime you write hydrogen into a formula, it must be written as H2, or into an equation, it must be written as H2. Okay? Anytime you write oxygen into an equation, it must be written as O2. Then why does that not say H2O2? I said oxygen written into an equation. Is this oxygen being written into the equation in H2O? No, what is it? It's water. It's no longer oxygen. It's a new molecule. Okay? If we have oxygen all by itself, then we'll call it oxygen. The instant it's bonded to something else, it's no longer oxygen, it's a new compound. Okay? That new compound is going to have different rules for how we balance out those charges. That comes back to nomenclature. Okay? And that comes back to that nomenclature video, which in theory you all kind of watched. So if we threw this up and said, quiz time, y'all be good? Okay. So should we take a second? You guys want to try and do this on your own first, see how far you can get, and then I'll walk through them? We can set it up as a race. I've been in a really racy mood this. That's not quite the phrasing I wanted. Okay. I've been in a competition mood as of late this week. Okay. Do we want to set it up as a competition? We could even do it right side, left side. Now? Okay.
I don't even think I can answer.
Okay. We can approach this in a couple different questions that we could ask. Okay, so the question that you were all probably answering is, what is the name for the first two, and what is the formula for the last two? And those are valid questions. But I could just as easily have asked, what class or nomenclature class is that compound in? Okay. Which you might be, well, I don't really know what that means. If you don't know what that means, providing the name for the first two is going to be really, really hard, because you don't know what rule set to follow. There's 5 different classes. If you don't know which class you're in, you don't know which rules to use, you will probably get the name wrong. So make sure you can identify the class. So for this first one, it is binary ionic. For the next one, I always forget what they call this one. I think they call it covalent. Sometimes you'll hear it molecular. Binary molecular. I think that's what your textbook calls it. Right. The next one down, also binary molecular. And the last one is ternary ionic. Right? So let's look for the key things that would allow me to quickly identify these things. Bi means 2. How many elements? 2 elements. Not how many total atoms are present, how many elements. There's only 2 elements, so that's binary. Okay? Ionic. When do I have an ionic bond? Metal and a nonmetal. Notice in our list of bonds we never mention metal bonds. Why? It's too hard. We don't want to deal with it. For me. Okay? So the instant I see a metal, it's got to be ionic. Well, chromium, because I did a really good job on my nomenclature, Justin, is a metal. So I know that has to be named according to our binary ionic rules. The next one. Okay? I know it's binary because 2 elements. I know it's molecular because nitrogen and oxygen are both nonmetals. Tricarbon dioxide. Well, carbon and oxide. The carbon should be easy. The oxide might be a little bit tricky, but both of those are nonmetals. If I've got only nonmetals, I'm looking at my molecular compound. Right? The last one, ionic because we have lead. Ternary because I would actually argue I wouldn't even go as far as saying acetate. I would go as far as TE. And I would change that because the E shows up in a lot of places. T. I know it's ternary because I see a T there. Okay. If it wasn't ternary, if it was binary, I would likely see instead of a T, a D, okay, for it being a binary ionic compound. So if you see a T there instead of a D as in dog, you're likely looking at a ternary. It's not perfect, but it's pretty darn close to perfect. Okay? So I've now classified the compounds. Now that I've got the classifications, I can deal with naming them. Okay? Because I've got all the rules memorized. Do you have the rules memorized yet? No, so pull out rules and use the rules. Okay? I don't expect you to have them memorized right away. I expect you to be working with those rule sets until you do get them memorized. So let's start with our binary ionic up at the top, Cr2O3. Okay, let's actually do the timing now on me coming up with the fully correct name. Okay, so I might need a little bit of time here. Let's see. We can delay a little bit because we get out to a round number here. If you've got a bunch, purge as much information as you can that you know is correct. Don't worry about getting the whole name there, but get information down that you can then later use. Right? So this is what I would mean if I had to name all of these. Sorry, I can't go fast and talk at the same time. Give me 2 more seconds because I dropped the pen. Oops. Oh. So a minute. It's not bad. Kind of slow. I apologize. I'll get better. Okay. And there we have all of our names. Where did I start? Started with the easy parts. Okay. Started with the part that I was told that I needed to memorize for Unit 1. Like the symbols and their names, being able to go back and forth. I know Cr is chromium, so I wrote out chromium. Did I spell chromium right?
Yeah, I think so.
Probably. Do you need to worry about spelling?
Hopefully not.
Hopefully not, since your exam is largely multiple choice. You probably don't need to worry about spelling because I'm not going to waste a multiple choice answer on misspelling something. Okay. O I know is oxygen. Because I knew some information about the binary ionic compound, I immediately converted the suffix over to the "-ide". Okay, the next one, I had nitrogen and oxygen. Again, I knew what the suffix was supposed to change to, so I'd already swapped that across to the "-ide". The next one down, all I specified was carbon and oxygen. Okay. Arguably, I probably would have done that one all the way through. Most students find the binary molecular to be trivial is a bit of an overstatement, but relatively quick and easy to pick up because everything is blatantly told to you. You don't have to do any kind of thought. You just write down exactly what it tells you. Right? And then for the last one, I specified what the symbols were, okay, for lead and for acetate. Acetate may have been a bit tricky for most of you because you probably haven't memorized your ternary compounds. Okay? The ternary compounds you will have to memorize just like you were supposed to have memorized the elements on the periodic table. So you will match the name to the formula. Okay? As we went back through, I think I went through and did the easier binary covalent or binary molecular ones. The di for nitrogen because it says 2 nitrogens. Di is the Greek prefix that I use for 2. I use pent, and you'll notice I even put pent with a question mark on it. I know it's pent, but I don't know if it's pentaoxide or pentoxide. And quite frankly, I don't care. Is that close enough that I would be able to get the name in a multiple choice? Yeah. Is it close enough that even if it wasn't multiple choice, the grader would have a hard time taking points away from me? Yeah, probably. Okay. Just enough that I've got the information without getting that specific and wasting my time and getting it perfect. Okay. The tricarbon dioxide, tri means 3, so I specify the 3. Di, 2, and I've got those names nailed down. You'll notice that I ended with the binary ionic and the ternary ionic because those two are harder. They take a little bit more practice getting used to building those structures. And it's going to come from what extra information is specified. What stands out as different for the names in our ternary ionic compounds? If we look at the name, the name for C2O3, we look at that name in the upper right-hand corner, and we look at our lead-4 acetate in the lower left-hand corner. Why do those stand out as different than the tricarbon dioxide and the dinitrogen pentoxide? No prefixes. That's an interesting thing. What'd you suggest?
They're using numerical values instead of like chi or di.
We're using a Roman numeral. So we have a Roman numeral that's all of a sudden popping up, and we don't have prefixes. So let's summarize the meaning of those things at the bottom here. What does the prefix specify? This tells us the amount of that element. What is the Roman numeral? Oh, that's a really long word. What does the Roman numeral specify for us? It specifies the charge. Very different meanings. Do we need to use different meanings? Yes, because if I use the prefix for all of them, well, then I'd have no difference between an ionic compound and a binary molecular compound. So what I'm trying to do is differentiate that. Why do I need to differentiate that? Because they have very drastically different chemical reactivities. So I need to have a nomenclature system that draws attention to them being different. Okay? So the middle ones are binary molecular. Hopefully you see those as being straightforward. You use the prefix as your amount. The one that you will probably struggle with would be the top two. Where would be our top two. So let's take a look at those. Or actually, as I do this, were there questions about the middle two?
Questions on all of them, but I'm not going to ask them.
Okay. So let's take a look at what's happening with the top one. You'll notice I've got a little bit of work there. Okay, for the oxide, I wrote -2 and I wrote 3. With respect to the oxide, do either of those numbers jump out as, hey, this is where you got that from, dude? What's that?
Roman numerals for 3.
Nope.
There are 3 oxygens, that's what
The 3 oxygens. Okay. The 3 that I've got from my formula is the 3 right there. It is the amount of oxygen. What's the -2? Okay. It is the charge on the oxygen. Because this is an ionic compound, okay, I'm required to be thinking about the charge of my elements. What did we just talk about like 2 slides ago? How about the charge on oxygen? Oxygen is a -2. That's why I put the -2 in there. You'll notice I'm missing a little bit of work to connect these, but we'll show that in a second. And the other work I've got, an X and a 2. Where did the 2 come from? It's the number of chromiums. What is the X?
Times 2.
It's going to be the charge on the chromium. And Logan, you said something interesting there. I don't know it. I look at the periodic table and I find chromium, element 24, somewhere in the middle of the transition elements. Am I required to know the charge on chromium? Why not? So one argument, it's the transition elements, and Mike said we just kind of don't worry about those. Well, I'll kind of accept that. We aren't required to know those charges because they go all over the place. Chromium can be a +3, a +4, a +6. Those are at least its common ones. Okay? It can also be a +2. Okay? Well, which is it? If it can be any one of those, I don't know. Okay? I have to determine what that is. That's what I'm setting up here. I'm setting up an equation to be able to solve for the charge on the chromium. That's why I have it as an X. Which brings up the next part. I eventually said what that X was. Said it was 3. It's the Roman numeral, remember? The Roman numeral is the charge. The Roman numeral I put up there was 3 next to the chromium. I've specified the charge on the chromium being a +3.
Did you say it was 3?
How did I come up with that +3?
Did you say it was 3 because the X could be 1?
If the X is 1, then the Roman numeral should be 1. It's not 1.
There's no charge on that.
Did you use that oxygen?
Yes, I use the oxygen. What are you suggesting, Melissa?
There's no charge. Like when you look at the whole formula,
If I look at the charge in the oxygen times the amount of oxygen, what am I totaling there? The charge contribution from oxygen. If I do the charge on the chromium times the number of chromium, what am I looking at? The charge contribution from chromium. What happens when I add the two charge contributions to each other? I won't quite accept B equals 0. You're technically right here, but there's a better term. It must equal the overall charge on the compound. Okay. For those of you saying 0, when it comes to the nomenclature chapter, yes, the overall charge will be 0, because we are assuming we are making neutral compounds. Okay. Why would we make neutral compounds? They're more stable. So when we're trying to build a name for a compound, the reason we can name it is because it's stable enough for us to actually isolate and hold on to. So more than likely, it will be neutral. Okay. If it's not neutral, where do we specify it? Even if it is neutral, where do we specify that information?
The top right.
The upper right-hand corner of our formula. What is written in the upper right-hand corner of the CR203? Nothing is written there, which means the charge is 0. So if I add the charge contribution from the chromium to the charge contribution of the oxygen, what must those two things equal? The overall charge on our molecule, which in this case is 0. And I get X equals a positive 3.
Wow.
X is what I was substituting into this equation for the charge on the chromium. Where's the charge specified? As a Roman numeral in my name. Okay? This is one thing that I will be changing this semester due to consistent feedback from students. I, with a passion, hate nomenclature. Okay?
Why?
Because it requires a rule, and you have to memorize that rule. And my memory is as good as a steel trap, a bear trap, something like that, with lots of holes in it. Okay? I cannot memorize things.
Bowl of water and a colander?
Sure, a colander. I'm really good at whatever. Some analogy with lots of holes in it. That's my brain and nomenclature. Which means when it comes to remembering the rules, I have notoriously a bad memory for it, and I don't do very well with it. Okay? When I went through and took chemistry, I looked at the value, the point value of nomenclature, and said it was 10% of my grade. I don't need that 10%. And I accepted it as a loss. Okay? You are more than welcome to do that. Just realize you have to live with the repercussions. I scored an 895 out of 1,000 points. That comes down to a B. You do the math on that. Nomenclature was the difference between an A and a B. Okay? Because of that, I also don't make nomenclature worth quite as much. Just as kind of retroactive. But it is super incredibly important. Okay? And the biggest part of this is not so much how do we make the name, because the name isn't that big of a deal. The big part about this is the part that I heard everybody go, oh, crap, when you looked at all the formulas and the calculations coming out of it. The calculations, the formulas, and how we come up with the charge and the amount of each of those elements, that is the part you need. The part that you don't want to do is the part you need for all of chemistry. We will keep coming back to that. Okay? We are officially done, but for the sake of the video, I will record out how I did that last one with our lead acetate. You'll notice the work I specified. You can pack up. I'm going to try and talk into the mic, though. Is lead. Remember, the charge must come out to be equal. So the number of lead times its charge. That's supposed to be a Roman numeral. That's close enough. Plus the number of the acetate times its charge must equal 0 because it's a neutral compound. Okay? At this point, I don't know the number of lead and I don't know the number of the acetate. So what do? I guess. I say that I have 1 lead. If I have 1 lead, this becomes 1 times 4 plus x times minus 1 equals to 0. When I go through and try and solve this out, what do I find? X equals 4. Is 4 a whole number? Yes, I found an answer that works for this. Lead is 1, acetate is 4, done. What if I'd guessed wrong? It wouldn't have come out to a whole number, and I would guess again.